right, everybody, I'm really excited to introduce our next speaker, Cindy Xiao. Not only am I a fan of their Binary Ninja plugins, they've also been one of my go-to resources for questions about the malware analysis process. I'm much more of a vulnerability research person by background, and so it really helps to have smart people that you can ask questions about the things that you don't know. And most importantly, though, they were the highest rated talk by our independent review board. We had 6 members of the community who reviewed all the submissions in addition to Peter and I. Rust malware analysis really is a hot topic right now, and we're super happy to have Cindy Xiao here to tell us everything we need to know about reversing Rust. So come on up.
Hello, everyone. Really excited to be here today from Canada. Came a long way here, so we got a lot to get through, so let's get started. Hi, my name is Cindy Xiao. My pronouns are she, her, they, them, and I'm currently a senior security researcher at CrowdStrike. Today we're going to talk about reverse engineering Rust binaries, specifically reconstructing Rust types. So I'll go into a little bit about my background, introduce myself, just so you can see where I'm coming from and what my current research focus is. So right now at work, I do malware analysis and malware reverse engineering for cyber threat intelligence purposes. Before getting into InfoSec, I used to be a C and C++ developer, so I'm often interested in looking at things from the developer's perspective a bit when I'm reversing. On a practical level, over the past few years, we've been seeing more and more Rust malware in our analysis queue, and we just didn't really have any practical skills to deal with them. So kind of since 2023, I've been using some time to work on this topic. That picture of me is from a lightning talk I did at Recon a few years ago about Rust in the Windows kernel, and I have various other blog posts and plugins and stuff that I've released since then. So I want to talk a little bit about where we're at in 2025 with reversing Rust. We need Rust RE skills for, it seems like I get a new malware every week now in my queue that's written in Rust. And it's everything from ransomware to info stealers to remote access tools for both e-crime and targeted intrusion actors. We're also seeing that legitimate software, right, is being either rewritten in Rust or are having new components being written in Rust. So this includes Windows, parts of Windows, new Windows drivers, Android libraries, and a lot of things that maybe you would have written in C or C++ before. So what do we have on the reverser side? Not that much, still. We have some function signatures, right, for the standard library that you can get. Some of them are shipped with IDA now. We have the ability to generate function signatures for third-party libraries. There's a tool called RespBinSign that I really like for doing this. And I think most of us have a good understanding now of if you just run strings on a Rust binary, what do all of these strings mean? A lot of that is metadata. A lot of that can give you useful information as well. And I did a workshop about this last year about this topic, so you can go check that out. But what we don't have still is tools for reconstructing Rust types or marking up Rust types well when doing static analysis. And we also don't really have a lot of good educational resources on just systematic explanations of static Rust reversing. Nothing that's really thorough and goes through stuff step by step. So this is my attempt to fill that gap a bit. Just have this fun little anecdote here. So the Rust compiler is documented in an online book called the Rust C book. So one of the features, of course, that's documented is all about, well, stripping debug info. And the Rust compiler developers, I think, they think that we can do more than we actually can, where they say, well, you can't use strip as a meaningful security obfuscation measure because disassemblers and decompilers can clearly still extract considerable information, even if you don't have symbols. And I sure don't feel that way when I'm looking at a Rust binary still. All right, so we're going to cover this in kind of 4 blocks today. We'll start with just the basic Rust types from the programmer's perspective. This talk is intended for people who have never written Rust and who don't know Rust, but who maybe have reversed other languages before. So we'll learn a little bit of Rust together. Next, we'll look at things from the other side, from the compiler's perspective. How are these types that we've just looked at actually laid out? We're then going to construct some standard library types from those building blocks and put all those things together. And finally, we'll look at some features inside Rust binaries that can give you hints or information about type layout. Our sample that we're actually going to be looking at today, that I've used for all the slide examples, is a piece of malware called Rusty Claw. There's nothing like super special about it. It's just another downloader. There is a lot of very similar Rust downloaders like this out there now. But it is a publicly available sample. I'll put the slides up on the internet afterwards, and you can download it from Malware Bazaar and follow along afterwards if you like. And it's just a x8632 Windows binary. Specifically, we are going to be trying to annotate the code inside just this one basic block as much as possible. So I'm going to zoom in a little bit here, but there's a conditional check, and then if this conditional check passes, we go and call a function, and maybe there's some string data being passed inside this function, and we don't really know what this is or what this means or what any of these types are. And this is just a screenshot from the Binary Ninja decompiler. Just once you open the binary, do the initial auto-analysis, this is what you see. So I find that from me talking to my colleagues and from other people in the industry, right, like we all still even have trouble with something that's this simple. So we're going to try to get into it a little bit comprehensively. This is a spoiler, it's a preview of a nicely annotated, kind of all marked up version of this, where I've applied some types. There's some fields that are being assigned here, and I've marked up the names and types of the arguments that are actually being passed in here. So we'll try to get close to here. We'll also be reversing kind of the body of the function call inside that block. It actually ends up being a Rust standard library function, but we'll go from something like this, just when you open up the decompiler, or similarly, if you open up IDA, hit F5 in this function, to something that's maybe a little bit more like this. We're marking up those standard library types. Okay, so let's get started into our first section here. Let's learn a little bit of Rust. So I cannot teach you all of Rust in less than 1 hour. That would be impossible. But we will need to understand some Rust source code. There's kind of two practical reasons for this. The first is that Rust is a really different language from C. And our decompilers still mostly emit C or C-like representations. And we're going to need to take that C-like source emitted by a decompiler and try to think about what this would have looked like originally in the Rust code. Second, the Rust standard library and the Rust compiler are both open source, and they are both written in Rust. And these are actually really great resources to go and read if you're trying to figure out how something works. I find that it's reduced the magic for me a lot, where I'm not kind of just like guessing or relying on heuristics. I can actually go and read the implementation of a standard library type because it's all right there, it's all open source. But in order to do that, you have to be able to read a little bit of Rust. Okay, so crash course now on some syntax. This is a variable. It is called counter. I'm going to zoom in a little bit here, so maybe small from the back. It's of type U64, which is Rust's unsigned 64-bit integer type. A function looks like this. It's pretty straightforward here, where we have one parameter named input, also of type U64, and this function just returns a U64. And the function call looks kind of how you would expect as C. We can also have generics in Rust as well. So with this angle bracket syntax here, this generic here is the std_vec type, which is very similar to your C++ std vector. It can be generic over the type that it's holding. So in this case, this is a vector of U8s, which is basically unsigned bytes. Of course, we can also have references. So if you want a reference type here, you specify that with an ampersand. And if you want to take a reference to actually pass into that function we just defined, you can also use an ampersand. So very basic syntax stuff. And just another review of some of the basic types. The integers are named kind of like how you would expect. You can tell the size and also the signedness just from looking at it. There's also a pointer size type, so called usize or isize, similar to your size t types in C. And we can also have fixed-sized arrays. So this is just an array with 128 entries of unsigned 64-bit integers. Now, I know that some of you actually do know Rust, and you might be like, oh my God, Cindy, where are all like the keywords? This is not real Rust source code. So I have simplified some of the examples in this talk, just to make it easier for people who don't know Rust. So remove lifetime annotations, removed a couple of keywords, messed around with namespaces a bit. But we're also mostly not going to talk about some like really important concepts that you would need to know if you're a Rust developer. So we're actually mostly not going to talk about the borrow checker like at all. Lifetimes, mutability, unsafe, all of these things that make learning Rust really hard. We can mostly ignore those today because these happen like during the process of, all of these are checks that happen during the process of compilation, and they mostly don't affect our type layout today. So here is a meme about how hard the borrow checker is. All right, so let's get into some more interesting types that are maybe a little bit different than what you would see in C or C++. So Rust has a type called a slice. This is a special type of reference. It's a sized view into some collection of data. So for instance, if we have some array of bytes, we can take a sized view into that array where we say, okay, take this view into some array that has unsigned 8-bit integers. So this is a special type of reference because it contains information about not only the start of that view, the address of the first element, but also about the length of how many elements we want to slice. So here's a concrete example here. So suppose we have some fixed-sized array of bytes. We can take a slice of 2 values from that array, starting at index 1 with the syntax here, and we can go and print those contents out. Since the slice also holds information about its length, so it's a sized view, you also have the size of that view, we can also go and query that length and print it out again here. Next we'll be talking about strings. If you've written Rust, you might know that there are like a million string types in Rust. We will be focusing on just 2 of them today. One of them is the primitive type answer, which is also called a string slice because it is just a type of slice. It's a reference or a sized view to some static string data that exists somewhere in your binary or in memory. And also the standard library string type, std string. So it's your typical global heap string type. So where will we see string slices? There's kind of 2 places that are quite common. First is string literals. So this is like similar to your static const char pointers in your C programs, where the string is just embedded somewhere inside the binary. Next, you'll see it in slices of the standard library type, std string. So in this case, this is my global string of just my name, and we can take a slice of that from index 0 to index 5, and we can query the length of that slice as well as print out the data inside that slice. So it's really just another type of slice, which we just covered. A concrete example of where you'll see this as well is if you run strings in your Rust binary, some of the strings that you're going to see are a bunch of what looks like source code paths. This is actually something called panic metadata or panic path metadata. And inside binaries, they show up as string slices, where they're structures that consist of a pointer to some string data. In this case, this source is Windows 7 or below.rs, and the length of that string data. So this is really useful for if you want to slice up those static strings, right? Because that length information is there, and because Rust strings are null terminated. And I have some previous work on this that you can check out as well, including a Binja plugin that helps you out with slicing some of these. All right, so next we'll look at the std string type. So this is our first example of a Rust struct, which are also like very similar to structs in C, C++. So our std string is actually like a really thin wrapper over that vector type that I mentioned, and it ends up just being a blob of bytes consisting of a pointer, a length, and a capacity. And this is kind of the equivalent C-like representation of that std string type. So pretty similar to growable heap strings in other languages. Now we're going to talk a bit about Rust enums. And this is a type that works quite a bit differently than enums in C. If you're familiar with the term like tagged union or like the C++ std variant, this might be familiar to you. But as you know, in C, we can have unions which can hold many different types of data, right? But the union itself doesn't hold any information about what variant of that data is actually currently active. So if we have a union like this, and we're using it, we don't actually know if what's inside is this OK data variant, which is an integer, or this air data variant, which is a car pointer. And usually you need like some other metadata that you pass around to tell you like, okay, this is currently an OK data, or this is currently an air data. Rust just combines both that metadata that you would usually need to carry around and the union itself into one concept called enums, where in this case, this is a tagged union that can either contain a 64-bit integer or a string. And the C-like representation looks like this, where you have a union as well as some integer tag that's attached to it. So another concept, I guess, in the Rust type system that's a bit different than C or C++ is traits. And this is how you do object-oriented programming in Rust, like very heavy scare quotes here. So this is very similar to interface types in other languages, where a trait is a certain interface that your concrete type has to implement in order to conform to that trait. So in this example here, we have a standard library trait called core format write. And this is a trait that if your concrete type is a Unicode accepting buffer, so if you're like a string buffer type, or if you're some sort of IO stream type, then it probably makes sense for you to implement this trait. So in order for your concrete type to implement this trait, there's some methods that you have to implement. So for example, this write stir method is required for your type to conform to this trait, and all it does is it will just append a string onto whatever your concrete type is, whether that's a buffer or a stream or what have you. So as an actual example, our standard library string type actually does implement this trait because you can write additional strings onto your growable heap string, right? And this is the concrete implementation right here, where we implement the write stir function, which takes in a string slice, and all it does is it just calls the std string push string method, which just appends that string slice onto your new string. So there's no concept of like superclasses or like subclasses or like really inheritance. It's just some interfaces that you can either implement or not implement. And the way that Rust actually uses this to do dynamic dispatch is we use another type of reference called a trait object. So this allows us to write generic methods without actually knowing what the concrete type is. So this is our equivalent of doing object-oriented programming in Rust. So in this example here, if I have a method that just does one thing, it appends the string woohoo onto whatever you pass in. But you don't actually need to specify a concrete type here. You don't need to say like, oh, you must pass in an std string, or you must pass in some IO stream type. You can just say, if this type implements this core format write trait, you can pass it in, and I'll know what to do with it. I can just call its write stir method. And so in this case, I just used an std string again. So I've created it here, and I can just pass it in kind of transparently. So that's what those traits allow us to do. One important trait that will be relevant for us later is the drop trait. This is somewhat special because this is how Rust, I guess, implements the concept of destructors, where if you have a type that when it goes out of scope, you need to free some memory or you need to close some resource, you probably want to implement this drop trait that goes and cleans it up and takes care of that, because the compiler will generate code that calls that trait when your type goes out of scope. So that's one place where traits are relevant. And this is just an example of the implementation of that drop trait for our vec type, where all we do is, in this implementation, we just go and deallocate the main pointer for the data inside that vec with this other wrapper function called drop in place. All right. So let's move on to the compiler's perspective about all of these types, now that you totally are very familiar with Rust and can recite all of those types from memory. So what does Rust actually guarantee about type layouts? Rust is pretty well documented, so there is a reference book that actually tells you all of these guarantees, which I've linked here, but I've picked out some of the more important ones here. So the sizes of your primitive scalar types, those are guaranteed. You know, exactly how large a bool is or how large a floating point 32-bit integer is. The sizes of references are also guaranteed as well. But there are different types of references, and each of those types of references has a different guaranteed type, guaranteed size, sorry. So a reference to your primitive types with those known sizes will just show up as a pointer. It'll be whatever your pointer size on your platform is. However, we also covered those two other types of references, right? Slices and trait objects. So a slice, such as our string slice there, or our slice into our byte array there, those carry additional information about the length of that slice. So that information needs to actually live somewhere with that reference. Similarly for trait objects, because trait objects, eventually we need to actually resolve that into some concrete type that we're dealing with, and we need to also resolve the methods that that concrete type implements to fulfill that trait. So there's also additional metadata there. So they're going to be larger than your plain old primitive type references. And of course, structs and enums have absolutely no layout guarantees about size or alignment or field ordering. The compiler can do whatever it wants. So let's take a look at some of those special reference types which have additional data. So slices include, we already kind of covered this in the panic path example, but they include a pointer to the beginning of the slice data, and there's some metadata attached to the pointer, which is the length of that data. So in this case, this just points to a string of size 17. Trait objects as well have both a pointer to some concrete data as well as some metadata attached to the pointer. So in this case, this is our core format right trait object, which we looked at in the last section. So this will contain both a pointer to the concrete type that eventually implements this trait, in this case, our std string, as well as a table containing the function implementations for that trait. So in this case, our concrete type is the string, and our trait table will look something like this. And this is essentially a vtable, right, like you have in C++. So this is a table of pointers, and it will point to, eventually, the concrete implementations of write_stir and write_char and write_format that that concrete std string type has. And I mentioned that your type layouts aren't really guaranteed. But what about when passing those types between functions, right? Is that somewhat guaranteed? Like, can you expect things to be in certain registers? Is there a nice API that we can just look up? And the answer is no. So for Rust to Rust function calls, the calling convention in the API is neither stable nor even defined and written down nicely somewhere. Often what ends up happening is that the compiler will just end up using one of the platform's usual calling conventions, but this is not completely guaranteed. So in our Rusty claw binary, which is our sample throughout this presentation, in this function call, you can see that this is sort of Windows x86-32 fast call, where we have, let me just zoom in a little bit here, where we have some data being passed in an ECX and an EDX, and then everything else is just pushed onto the stack, and those do end up being our first two arguments, but as we'll see, this doesn't necessarily completely correspond to our nice complete Rust type. Because this is actually a string slice that we're passing here. If we were looking at the Rust source code, it would look something like this. The slice data is this message here, and this is the length of that string. But here, this is actually split across our two registers. So the string data is an ECX, and that length is an EDX. So why is this? Well, the Rust compiler is a bit complicated, but I will attempt to simplify it through this diagram. Now, I know this diagram is very small. Do not worry. I have a larger version that is zoomed in. This is a very simplified rendering of the Rust compiler pipeline. So if you're a compiler person, please don't like yell at me after for this. But I want to kind of demystify a little bit how we go from the source code to our complete binary. So suppose we have some function here called foobar, which just takes a string slice as an argument. So you can, it's defined like this, and you can use this with something like this, so passing a string literal in. This Rust source code, during the process of compilation, gets turned into one of Rust's own intermediate languages called MIR. And in MIR, each of these types that we're dealing with has some layout metadata associated with it. So this is a compiler like internal kind of struct definition. This only really exists in MIR during the process of compilation. But this layout metadata contains some information about the size, about the alignment, but also about the ABI to use for this specific type. So an answer, the string slice here, actually ends up having an ABI internally in the compiler of scalar pair, where it gets broken down into that pointer and that length that form part of the slice. And what the Rust compiler does with types that have the scalar pair ABI in the Rust MIR intermediate language is when it lowers that to LLVMIR, and it notices that, hey, we're going to pass this type into a function in some function call, it will just try to split them, right, across two different arguments, even before we get to the assembly level. So in this case, this is the definition of foobar in LLVMIR, where that string slice has been split across two different arguments. And then LLVM mostly takes care of lowering to our assembly level here, where these get passed in two different registers. So that's a very, very quick introduction to what's going on there, but you'll notice that pattern a lot, where if you have a reference with some metadata, with both a pointer to some data and some metadata like this, it will just get split across two different arguments, and then those arguments for whatever platform you have will get split across two different registers or two different stack locations or what have you. Okay. So now let's talk a bit about how enums look from the compiler side. So recall that enums are Rust's tagged union type, And they consist of something that's very similar to your C-like union and also an integer discriminant. So this is, again, our standard library result type, just kind of repeated here. But what ends up happening is that you often see an idiom that's very similar to this in decompiled Rust binaries. So this is because the standard library result type is actually used quite often for error handling in Rust, where you can either have, so it's better with the concrete example here, but suppose we have some function that reads some data from the file system. So in this case, this stdfs read inner is a standard library function that reads from the file system and can fail. What this actually ends up returning is a result type, which can either contain a vec full of the nice data that we've just read from our file, or it can contain an error string that tells you, oh my god, I can't find this file, like, help. So the way that we distinguish between them is by the tag on the union, which is part of the Rust enums information. So you'll often see this in decompiled Rust binaries, where you do some function that can fail, right? That returns that std result, and then you check what variant of data is inside that tagged union. You do that by checking that discriminant, so the tag on the union. So in this case, if the discriminant is this value, then we know that, okay, this read failed, and you do some error handling. In this case, you just panic and end the program, and you print out this message here saying what happened. And otherwise, the read was successful, and you can continue on. I actually don't know exactly why this is, but the discriminant value that Rust often ends up choosing ends up being this very large integer with 1 bit set. So you often see this like OX8, a lot of zeros used as a discriminant. So in our Rusty Claw example, with that like one block that we're trying to reverse, that's actually exactly what's happening here, is result is actually some Rust enum value, which can either be a successful value containing some actual data, or an error value containing some error message. And what's happening here is we're just checking the discriminant on that result enum. And in this case, if we go into this branch, that means that whatever operation we were trying to do above this has failed. So we're actually going to call this function right here and print out that same error message as in the last slide and actually exit the program. So this actually doesn't ever return. Okay, so let's put some of those basic building blocks together now that you know a little bit about like the basic types, you know a little bit about their layouts, about what all is inside them. We're going to construct a very important standard library type that comes up all the time called core format arguments. It puts together a lot of like the concepts we've looked at so far, and it's useful because it's used for string formatting in Rust. So this is how you do string formatting in Rust, kind of from the, I'll zoom in a little bit here. From the programmer's perspective, there's this print line macro that you can use that works like very similarly to every single string formatting function in every other language, where you have some literals, and then you have a placeholder for whatever value you want to put in, and then you have another literal and another placeholder for another value. So it's quite easy from the programmer's perspective. Another place where string formatting shows up that doesn't necessarily require the programmer to do anything is when aborting or panicking the program. So this is just an example from the Rust book, again, which is one of the sources of how to learn Rust that's online, where we do some operation here where we open a file called hello.txt. And what this unwrap method call does is it says, if you can't find hello.txt for some reason, or if you can't open it for some reason, just exit the program and print a nice error message. And that's called panicking in Rust. So if I run this, since I don't have hello.txt anywhere, what's going to happen is you'll see this message be printed out. with some metadata about where exactly the program crashed, but also some information about what the cause of the panic was. So you'll notice that this includes some static data here, right? So it says called result on wrap on an error value, but also it includes some data that is dynamic. So in this case, this will change depending on exactly what happened here, on what the cause of us not being able to open that file is. So this is what the implementation of formatting that message looks like under the hood. So this is our core result unwrap failed function in the standard library that just says, hey, if you have a result that contains an error, just print whatever is inside that error and then exit the program. And the way that this works is using another macro called panic, which is actually very similar to that printline macro that we just saw. It will also take some formatting specifiers and some placeholders and some string literals in between and give you a nicely formatted message out of them. Let me zoom out here. So under the hood of all those macros, you don't need to worry about like the definition of a macro there. I just want to show that this printline macro as well as that panic macro end up just calling a function called io:_print. And what that takes in order to do its work and to format your string for you is it takes a struct called of type core format arguments. So let's now look at the core format arguments type. If we hadn't gone through like all of that before, you might be looking at this and like being like, oh my god, what do all of these ampersands mean? Like, I'm very confused and dismayed. But we can go through it together step by step. So it has 3 members here in the struct. First is this pieces member, which is a array slice, right? That's what this ampersand square bracket syntax indicates, containing string literals. So remember that we had an array slice before containing a U8, that was just a slice of bytes. Now we can have just a slice of string literals. That's all that this means. And if you were to print out the data that was inside this slice, it would look something like this. So these are the static parts of the string that we're trying to format. This is, again, our first number is 86, second number is 64 example. Next, we have any formatting specifications, such as like, you can have like nice columns, you can have alignment and width and so on. Sometimes these are used, but often they're not. And finally, we have an array slice, again, with this ampersand square bracket syntax, containing the dynamic values that we actually want to format and that we want to display as strings. In this case, are 2 integers here. So again, the and stir is an array slice, which contains a collection of literal strings, which are string slices. And it's going to look something like this, where suppose we have 3 string literals here that we want to represent. We're going to have a pointer here as the slice data that points to the beginning of where those string literals are. And then we'll have this length here that says, okay, once you've gone through this many string literals, please stop. That's not part of the slice anymore. And then, of course, each of these string slices is itself a slice. So each of these is then, again, a pointer to some string data and the length of that string. So that's a breakdown of what this would actually look like. That middle field there, which specified things like alignment and width. I mentioned that often, like, you don't really care about printing things in nice columns, right? You don't actually care that much about specifying the formatting further. And that's why this actually ends up being an std option. So a option in Rust is another standard library type that indicates either you have something here and it's actual valid data, or you don't have anything here and there's nothing inside this union for you to look at and you should just ignore it. So in this case, we have an option that either contains nothing or it contains the formatting specifications that we want. And again, this is a slice pointing to a collection of these structs. And this is what that option would look like, where you have, again, the tag on the union, the discriminant, that tells you either there's nothing here, there's no valid data, you shouldn't expect a placeholder here, or there's something here, there's some valid data, and there's a placeholder here, and it ends up being a slice, which points to more data. And the last field there is our core format argument slice. So again, this is a slice containing a set of core format argument structs. Now, what's inside each of those core format argument structs? So each of those, this is a definition here, each of those contains a reference to the actual value that we want to format, as well as a function pointer to that points to a function that says, this is how you format an integer, this is how you format a string, this is how you format, my cool IPv6 network address type, and so on. This is kind of the equivalent C-like representation of what that would look like, where you have some pointer to some value that you want to format, as well as the pointer to the formatting function. And it would look a bit like this, where you have a slice there that points to the first element of that collection of arguments, and the length here, which is the number of arguments that we have. And each of these, of course, points to our concrete value that we want to format, as well as the formatting function. And this is just a breakdown of the C-like representation of this entire struct. So this is like something that the programmer can write one line of, and it will generate a struct that looks like this. And I think this kind of illustrates why it's important to be able to read the implementations in the standard libraries, in the standard library of some of these things, and also to understand some of the basics of Rust types. Because without understanding like what this means, right, you would never be able to get anywhere. And that's kind of my diagram there of the full breakdown. So quite a large struct for something that's just a simple concept. So if we go back to our malware example here, inside this block, we're going to go inside this core result unwrap failed function. So this is what it looks like kind of immediately, just as we open the binary and do the initial decompilation. But recall that what this core result unwrap failed function does is, if we go back all the way to here, it does string formatting, right? We're going to have an STT argument that contains the string literal with the colon and the space there, as well as these two arguments, this message and this error that we want to format. So if we actually look inside the disassembly of this function, we can actually spot some things that actually look like likely core format argument variables. So recall that our core format argument consists of a pointer to some value, as well as a function pointer to the formatter function for that value. And that's exactly what this is, where we have some struct being constructed that consists of some value, a function pointer, some value, a function pointer. So if we define a core format argument like this in our decompiler, we can start to reconstruct this particular struct. So I've named these as well, argdata0 with its value and formatter function, and argdata1. And there's two of these that are right next to each other in this ESI variable. We can also see that these are actually both collected together into one slice. Right here, this ESI variable that we've constructed up above actually ends up getting put into this other variable here, along with an integer value of 2. So this is what that core format argument slice looks like. If you recall from a few slides ago, we have a pointer to that slice data, which contains a core format argument, which contains the beginning of a collection of core format arguments, as well as the length of that slice. If we actually apply that type and mark that up, we can start to see that this slice has some data, and that data points to this collection of two values and formatters that we had here. And the length of that is 2, because there's two values here that we want to format. And if we start applying some of those standard library types and understanding how they're laid out, we can actually start reconstructing what the logic of this function looks like. So this is going back to the decompiler after we made that markup in our disassembly. All right. Okay, so now that we've gone through what the types look like from the source code side, what they look like from the compiler side. We've gone through just an example of a standard library type. Let's look at some other features that can help us out with the specific layouts of those types. Because recall, we don't really know what the field ordering is. We also can look at, we have all these standard library type definitions, but it's maybe unclear how they translate still specifically to the binary. So one thing that does help with this is that there is a global allocator that Rust programs use. If you're doing a heap allocation for any standard library type that lives on the heap or requires heap growth, you need this global allocator to be defined, and luckily the Rust standard library provides a default allocator implementation. So the details of this vary by platform, but for example, here's the standard library's global allocator on Windows. And there's a bunch of details here, but in the end, it just calls heap alloc, which is your 132 heap allocation function. So every type or every function that requires an allocation will end up just calling into this one place. Similarly for deallocations. So you'll recall we talked all the way back at the beginning about our drop trait, right? That's how Rust implements destructors. So when a type goes out of scope or when its lifetime ends, the destructor of that type is called, and often that requires doing some deallocation. And of course, the Rust standard library provides a default global deallocator as well, which also varies by platform. And this is some of the details of the global deallocator. There's a stub function that will live in every single Rust binary that requires heap allocations. And at compile time, this stub just gets replaced with the system-specific, with the specific standard library allocator that you're using. And on Windows, this is what that deallocator implementation looks like. Again, there's a bunch of details here, but eventually it just ends up calling heap free. So you can actually look for these inside your binaries as ways to find where the destructors for your types are. But there's another actually really convenient way to find destructors for types, and that's via trait objects. So recall we had our core format write trait object, which is the way that we could do dynamic dispatch, where we didn't need to know our concrete type up ahead of time. Recall that it includes a pointer to a concrete type that implements that trait, as well as metadata attached to that pointer, which points to your vtable for your type's implementations. This vtable actually has a fixed layout, and it actually has some really useful metadata about the type that can help us not only find the destructor, but can also help us find the size and alignment of that type. So I've included a link here to the place in the Rust compiler where that vtable layout is defined and generated. It is somewhat fixed, but here's what it actually will look like. So I've been using the std string implements the right trait throughout this presentation, so we'll do that again here. But the vtable layout always starts before we actually get into any of the function, the pointers to the concrete implementations of the trait. It always actually starts with these three fields right here. A pointer to the destructor for the concrete type, the size of the concrete type that implements the trait, and the alignment of the concrete type that implements the trait. And these are actually used like elsewhere by Rust, by like some other standard library functions. I think the compiler uses these at some point during compilation as well. But this is useful metadata that's going to live inside your binary. And you can actually find these fairly easily once you recognize what they look like. If you have a function pointer followed by two of these like sized constants, which are the size and the alignment here, followed by some more function pointers, which are your type's trait method implementations, that is probably actually your trait object table. You'll also probably want to ensure that the first function pointer is actually a destructor, so you want to make sure that it actually does call this global, the allocator functions. So I have an example here. This is just an x86-64 binary with symbols, but it starts off with this function pointer to this destructor for string, and then these two integers here, and then some more function pointers. So I actually have a small script that I wrote just to go and try to find those trait tables. So this is Binary Ninja just on our malware sample that we've been looking at. And you can see here, this is actually already a candidate where we have a function pointer and then two integers here. So this is a 32-bit binary. Each of these are 4 bytes long. And some more function pointers here. So you can already kind of see what's happening. And if I run my script, that will just mark these up into a nice little vtable right here with the destructor pointer, the size of this concrete type, the alignment of this concrete type, and each of these implementations. And you can see as well, I've got some bookmarks here, that these show up like all over the binary, where you have more of these drops here for stdvec, and more of these specific trait methods. So there's more tables like this here, and so on. Most of these just have like 2 or 3 methods in their vtable. All right. So to finish up here with our example, we're going to go back to that core result unwrap failed function. So again, we looked before at this part of that function where we're doing the string formatting. Now we're going to look at what's actually happening here with the arguments that are passed in. Because you'll notice that one of the arguments is actually a trait object. So you can pass in anything that implements the format debug trait, and this function will still work. So what is the format debug trait? So this is defined in the standard library, where you can implement this trait for your type just to produce a very nice, convenient string representation when you're debugging it. So you can print out like the values, say, of all of the current fields. And it's just this little colon question mark syntax lets you do that. That's what this means right here, where we're taking whatever type is passed in here that implements format debug, and we're printing out a debug representation of it to help us out and to figure out why our binary panicked. However, this ends up being a lot of glue code, right? If you're just like, I have a coordinate struct, and it has 2 fields, and they're both integers. Now I'm going to be like, OK, print integer x, print integer y. The compiler can actually just generate a suitable one for you. There's a macro that the Rust language provides that will just generate some code for something reasonable, which prints the name of your type as well as the field values, if you just have a very simple struct like this. So if we go back again to thinking about, well, we have a trait object, right, that's passed in here. This didn't format debug. What does that actually look like? So again, it consists of a pointer to a concrete type as well as a pointer to the vtable for that concrete type's implementation of those trait methods. So what ends up happening here quite often as well is just as our string slice is split across two different registers quite often, right? Recall that it's that scalar pair ABI where the pointer and the metadata are split. For trait objects, the pointer and the metadata, so in this case, the pointer to the concrete type data and the metadata, which is the vtable, are also quite often split. So you'll often see, again, just the concrete type data lives somewhere and the vtable lives somewhere else. We're passing it in to a function. So in this case, I have a vtable example here. So this is our core result unwrap failed function call that we've been looking at. And this right here actually ends up being the vtable that's passed in. All right. So this is, again, we have a destructor here, the concrete, the size of the concrete type, as well as the pointer to the concrete implementation of the debug formatting function, which ends up being this function right here. And this is the vtable before I ran that script. You can see that it actually only has one entry, where we have the destructor here, we have the size here, the alignment here, and the one method implementation. And that's because the format debug trait only requires that you implement one method, which is just the debug formatting function. So this is the vtable that I've just showed. And if we actually start defining, because this method requires that you pass in a formatter struct, we can actually start defining that formatter struct itself. And the formatter struct here, it actually, so if we define just an empty type here called stFormatFormatter, we can actually start seeing just in the decompiler that there's some fields at offset 0x18 and offset 0x14 that are being accessed. And if we look back at the documentation for core format formatter, we can see that one of the fields is actually another trait object. So this is how you start to kind of see some of the indirection that's happening here, right? Where we want a generic method that just prints out a debug implementation of a debug representation of our type, and that generic method uses another generic method that actually does the writing to our output buffer to display our string. And again, that core format write trait is the one that we've been looking at throughout this entire presentation. It'll look like this with the concrete data type, with the concrete type pointer, and with the vtable. And if we actually just import this type into Binja or into whatever you're using and start marking that up, and also define the vtable type here, then we can eventually figure out that this last field with those offsets that are being accessed is actually our trait object here with that din core format write. And if we mark those up, what we eventually end up seeing is that we're calling this write string function with some string data, and that string data ends up just being the value null error. And the length of that string data is actually right here. So that's 8 bytes. So when we're printing out the debug representation of whatever it is that's being passed in here, the string null error gets printed. So what does that mean? So remember, again, that if you're a lazy programmer, right, you can just slap the derived debug macro on your type, and the compiler will generate some code for you, and that includes the name of the type and all of its fields. So in this case, what's happening here is that this is the default compiler-generated implementation for the debug representation of a type called null error, and it's just printing out its name right there. And because we had the vtable for the null error concrete type and its implementation of format debug, we actually have the size of that null error type already. So it's this OX10 bytes. And from that, we can actually start to define what a null error looks like. So it actually does end up being this standard library type called std_ffi null error. And this indicates that basically you are trying to construct a string that can be passed to, that's a valid C string, where the string actually is null terminated. But if you try to construct a string that contains a null byte in the middle, that's not really a whole valid C string, because in C, that means the termination of your string. So all this is the error struct that you get back after like you've tried to do something like this. So construct an invalid string. So because we know the size of that type already, we can start to define it, and it ends up looking something like this, where it's OX10 bytes, as we saw from the vtable. And we can start marking up this function as well. All right, so we are at the end now. That was quite a lot in the presentation there, and you might be wondering, like, how did I figure all this out, right? Like, how would I ever know all of this? I don't know any Rust. There's a lot that you can just figure out by reading the open materials that are available about Rust. The compiler is open source, the standard library is open source, and there's only really one implementation of each of those that's in place. You don't have like a bunch of different vendors with a bunch of different compiler or library implementations. A lot of these things about the guarantees, the layouts, the behavior of vtables, and so on are just documented and ready for you to delve into and read. So I think we're out of time here, but if you have any questions, please find me after. And you can also find me at the following social media links, and the seagull is how I feel all the time when reversing Rust. Thank you to my colleagues Ken, Josh, Lily, and York for listening to drafts of this presentation. Thanks to Reverse Review Board as well. And I have a list of resources here at the end with some additional details on what I covered in this presentation. Thank you so much.
Thanks, Cindy.